Okay, so I would like to start out my lecture today, and what I'm going to do is to explain stable diffusion, because you got the experience of stable diffusion or other text-to-image generation models in your homework 4. But however, how much do you understand the method? So I would like to explain it so that you can get the concept of what it is. Okay. And okay, so when we say stable diffusion, I would like to figure out it is okay. Let me show you something at first. It will clearly help us figure out what is stable diffusion. Okay, so let's see. This is the history of stable diffusion. Why is it named stable diffusion? Because there is a startup called Stability AI. So in late 2020, there is a venture capitalist. He founded Stability AI, use his own, mostly his own money. Okay, and in almost, let's say, and there is a professor in German, and his students called in the beginning they were in the Heidelberg University. Then they moved to another university, and they have their lab named COMFIS, Computer Vision Lab. What they did is one of their core member, a PhD student, graduated and found a runway AI company. And then they published a paper that is the high-resolution image synthesis. This one, okay, with latent diffusion model. So the first author, second author, and this is the professor. The first author and the second author contributed equally for this paper, and the second author is the founder of the runway AI. So you can see his name and the company names on the title of the paper. Then, okay, the second author, the first author joined Stability AI, so that they want to create something everybody can use. That is stable diffusion. Okay. So the Computer Vision Lab, they has two GitHub projects. One is latent diffusion, and another is stable diffusion. And okay, so let's see another comparison about the stable diffusion. Okay, so when we talk about the latent diffusion, it means the paper, okay, published in archive and CPR. And when we talk about the stable diffusion, it means the product delivered by the company Stability AI. And Stability AI not only deliver the stable diffusion model, and they also create a platform. So just like a DALI or something like that. The name is Stability AI. I forgot. Okay, let me check it. Let's see. Okay, Stability AI, I think. Stability AI platform. Not this one. Okay. Stability AI text to image. Well, I cannot find it right now. Okay. So do you remember I have a table show all of the possible choice for your homework 4, And one of them is the stability AI platform. Okay, just like a DALI or just Midjourney or something else. Okay, so you can see their release date. Both of them were in 2021, December. Okay, then what we use diffusion, easy diffusion is it is a wrapper. It's a try to create some script so that users can easily install and use stable diffusion. All right. So what we will talk about, what we will see today, mostly will be latent diffusion because it is an academic paper, and we can easily understand what is the effort to make it happen. And then the stable diffusion means, okay, because the trained model is very expensive. How expensive is it? You can see that. The founder of Stability AI, one day he released a Twitter. Okay, he claimed to train a model they use 256 A100 GPUs, and totally so many GPU hours, and it cost $600K USD dollars. Okay, so this is for, I forgot, for stable diffusion version 1.5 etc. So it is so expensive. It is almost, I should say, for a lab in a university, it's very difficult to use so much money to train huge models. But huge models are very useful for general users. Okay, so that's why the startup Stable Diffusion, they also contribute to academia research or all of the users. Okay. And okay, because it's very useful, so the company also raised a lot of money. Okay, so that they can keep doing research on it. Okay, so let's go back to our slide. Okay, so those are papers related to latent diffusion. Okay, and because there are so many papers, so I draw a figure. Right, so those points means papers or products released by those institutes, universities, or companies. Okay, so UC Berkeley, they contributed the DDPM. It is the diffusion model. The first diffusion model works for images. And Stanford contributes the DDIM. It is an accelerated version for DDPM. And Google, they contribute a transformer, VQ-VAE, attention, and VIT, and Imagen. Imagen is the Google's version, DALI. You can say this. Okay. And there are some other university in France. They prove the relationship between convolutional network and transformer. Okay. And OpenAI, the members in OpenAI are very active. They create a DALI-CLIP, DALI 2, DALI 3, and also they improve DDPM, and they modify the architecture used by DDPM, so that they claim the modified DDPM can perform better over games. And NIT, they contribute the CLIPDraw. It is an interesting application, and I will show it later. And the LAION, it is a nonprofit organization. It contributes LAION 400 million, LAION 5 billion, and OpenCLIP. Okay, so this is a text-to-image pair datasets. You use Stable Diffusion, and you just key in some prompts, and you can get the image. Why? Why your model can understand the meaning of your prompts. Prompts are just text, okay? Because there is a huge dataset, how huge. The 400 million is the size of the image and the text pair. So 5 billion, there are 5 billion image and text pair. So that if you change a few prompts, usually they can be found in the huge data sets. So that your model can know, okay, if I want a cat, what should a cat look like? If I want to say classroom, how a classroom should look like. So because they learn the relationship between images and text from those huge data sets. So, okay, so of course there will be some questions need to investigate. For example, if the instances in the dataset are very rare for certain text prompts, what will happen? Usually, because the machine just to learn the relationship. If there are very few instances to learn, usually the machine fail to generate the high quality images you want. Okay, so this is the computer vision lab in German, and Professor Omar, he and his students released 3 important papers: conditional networks, VQ-VAE, and latent diffusion. So this is the time of latent diffusion. It's in around 2 years ago, right? And then you can see there are several numbers: 1.3, 1.4, 2, 2.5, etc. This is the result of stability AI. They keep training the models and release those models. Okay. All right. Okay, and their relationship look like this. Okay. So for this track is the stable diffusion from DDPM, the first paper, and accelerated by DDIM, and then improve DDPM by tuning some settings. For example, because in diffusion model, there are many steps from a clear image to a noise image. So is it best to use a linear setting or other different settings? Because there are so many. So they investigated the problem in the improving DDPM. And they also, I should say, in DDPM, they use a UNet to estimate the noise. Okay, so that it can denoise. And they question, is their UNet is the best one? If they can they do anything to improve the UNet? So that is a problem addressed by this paper, diffusion model biscuit. Okay, and then the latent diffusion used the modified UNet. Okay, so this is the first track. And the second track is transformer. Google invented transformer, and then invent VIT. Okay, then VIT is used in CLIP. CLIP is the is the first image and text matching method. Okay, so from CLIP and but the CLIP use a private data set. Nobody else can use it. So the LAION project, they want to create a publicly available huge text-to-image data set. So they create a LAION 400N, and then they further expand the data set to become LAION 500 billion, and then they train another model called OpenCLIP. Okay. So what's the relationship between latent diffusion and LAION 400? Yes, because, okay, in the latent diffusion, they need a data set so that they can train the text condition model. And because LAION organization released their LAION 400 map, so it was used by latent diffusion. So this is the second track. Okay, and the third track is Google invent VQ-VAE. It is a vector quantized variational autoencoder. And then the Professor Omar's group used VQ-VAE to invent a method called VQ-GAN. It is image synthesis method. Okay, and the image synthesis method was used in latent diffusion. So the three tracks combine together and become latent diffusion. Okay, so let's start from, so there are three tracks, and then let's start from the transformer track. Okay, so what is transformer? If you, well, I should say, everything, okay, the term transformer was given from this paper. Attention is all you need. So this is Google DeepMind team. And transformer, it achieved the state-of-the-art performance on two translation tasks. So this is a translation task. It's not an image task. We will show, okay, so here it is still a translation problem. And here in this paper, some people try to use transformer or the self-attention mechanism for vision problem. And in VIT, okay, Google found a very effective way to apply transformer on computer vision problem. So thereafter, transformer become the state-of-the-art method for vision problem. Okay, but in the beginning, transformer is created for translation problem. Okay. So there are two data sets, WMT English to German translation and WMT English to French translation. So given the two data sets, there are 4.5 million and 36 million sentence pair. Okay, you have a lot of training data, and it covers 3,700 words or 32K words. Given so much data, how do they invent an effective method to translate sentences from one language to another language? Okay. And how to measure the performance of a translation problem? Okay, they usually call BLUE. It means bilingual evaluation under study. And this is the range of BLUE. Okay, if the higher the better. Right. How okay, if the score is greater than 60, then it means the machine can translate sentences better than human. And what is the meaning of the BLUE? Okay, it means it will calculate two penalties. The first is brevity penalty. It means the machine should not generate a very, very short sentence. Okay? If the sentence, so it means given an English sentence and a reference German sentence, then the reference German sentence is created by expert human. So this is we can assume it is a perfect translation. Okay. Then the machine see the English sentence and it will generate a German sentence. Okay, so BLUE means the comparison between the expert German sentence and the machine generated German sentence. Okay, so first of all, the machine-generated sentence should not be very, very brief. If it is too brief, there is no information contained in the sentence. So this is the first penalty. And the second is, all right, if machine generates a long sentence, how similarity is the generated sentence against the expert sentence? Okay, so they compare several n-gram overlap. So the n-gram overlap is if this is a sample sentence And 1 gram means just see individual words. And 2 gram means they will see 2 continual words from the sentences. And 3 gram means, okay, they will see 3 consecutive words. So it means if the generated sentence, they have the same words, so that is 1 gram. It means fine, quite good. And then they have many 2 gram sequence, means to be. So that means the order of the words are very, very similar to the expert sentence. And if the sequence is longer, 3 and 4. So if the machine generated sentence, it is almost the same as the expert sentence, then the blue score will be very high. So let's see the result. Okay. The performance for Google's transformer is 28.4. So let's go back to the score table. 28, it is okay. It's not very good. There are a lot of grammatical mistakes. And if let's see from English to French, then it is slightly better. Okay. But however, that was the state of the art in that year. So now you use ChatGPT and it translates English to Chinese or Chinese to English. Excellent. They use the same architecture. It is still transformer. The only difference is they create a very huge transformer. So what is the meaning of huge? Okay. Let's see this. So this is the basic transformer architecture. It is layer by layer. Okay. So here is a unit of attention mechanism. So if they stack, so this is, you can see there is n times here. So if you stack 1, 2, 3, 4, 5, 6, and if you stack several, let's say 10, 20, 30, or 40, the architecture will be very, very large, and there will be a lot of parameters because we need to learn the parameters for the in the multi-layer attention and feed forward. Okay, so now we can use very, very good translation because they create a very huge architecture, and they also enlarge the number of tokens. But so let's go back here. But in 2017, okay, when transformer was just proposed, they didn't use very, very large data set. Okay. All right. So that's here. No. Okay. So this means attention. So there is a query metric, key metric, and a value metric. When we generate the 3 metric, we will go through the attention mechanism, and it will generate a new sequence of a few sequence of specific token. Okay. So let's see an example. Okay. So this is, if I have a sentence, I have a friend who lives in Vancouver and often goes to Seattle, and this is N. Then we will convert the words into a sequence of vectors through word text embedding. Text embedding means I have a lot of words, but the machine doesn't know the word. So if I can convert those words into a space, so the space have some property. It means they will put a similar word close to each other. For example, maybe cat and dog the distance between the two words should be closer than cat and desk, right? So, and then, I should say, computer maybe should be close to machine, and the car close to trunk, and the tree close to flower. Okay, so they want to create a space so that every single word can be mapped to the space, and the space is meaningful. So this means input embedding. Then, because in a sentence, every word has its position. So it will encode from 1 to 15 into another encoder, so P1 to P15, and then concatenate the word embedding and the positional embedding to become a sequence of vector. Okay, so the A1 here, we will learn the WQ matrix to become a sequence of query vector, and then learn another matrix WK. It times the AI, it becomes another sequence of vector Q1 to Q15. Then we will compute the transpose of Q times K divided by the square root of the dimension. So we will get a lot. This means attention metric. And then for every column, we will compute its softmax. Okay. So, and finally, we will use a learned matrix WV to compute the sequence of vector, and then we use the coefficient alpha to create the vector of B, and then calculate the normalization and generate the new sequence of vector. So what does it mean? Here, we need to learn the WQ, WK, and the WV matrix. So this is learn the parameters. And also, the fully connected, there are also many parameters here. So here, this is the input sequence of vector. And through a layer, it will generate a new sequence of vector. So it's similar like to convolutional layer by layer. But for transformer, it is stack by stack. So it's like this. This is a VQK get in and get it. The output is also a sequence of vector. And the attention mechanism goes through several times. Okay. Then it will generate still a sequence of vector. And the sequence of vector will be used for the prediction for the output token. This look like this. Okay. If this is a Chinese, English to Chinese translation version, then in the beginning, for the sentence, I have a friend who, okay, then if I have a few words, 我有一位朋, etc. Then transformer want to predict the next word. Okay, so how do they do? They use the sequence. So the same. They do the same. This is also a sequence of vectors, and we also have the sequence of position. Then in transformer, we learn the WQ, WK, and the WV, and then we will go through another, using the same mechanism, we will get another sequence of vectors. So it is this, like this. So this is the English sentence, and this is a Chinese sentence. So go through several stacks. It will generate a sequence of vector. And then finally, we will compute the probability for all possible tokens. And we choose the maxima 1 as the token for the next word. So that is how transformer works. Okay. So go through those a lot of details. What are the message I want to deliver to you is the input of a transformer is a sequence of vector. Okay. And how can we see an image as a sequence of vector? Yes, we can. For every pixel, there are 3 values RGB, and we can vectorize an image into a vector. Right. So since transformer can work for translation, transformer can work for images, right? Intuitively, yes. But the problem is the computational load for a transformer is the order of n squared. N is the length of the vector. Okay. So here, in this example, if I only have 15 words, the order is the 15 squared. But for an image, if the image is not very small, then the number of pixels will be a lot. The order, the quadratic order of the pixel number will be very, very huge. That's the problem. Okay. So how to solve the problem? Okay. So in this paper, NIPS 2000, self-attention in visual model. And let's go back to the, okay, here, this paper. They propose a method. That means, okay, if transformer need to see through all pixels in the images, it is too expensive. So how to solve the problem? They just see pixels locally, just see pixels close to the central point, so that it can reduce a lot of computational load. Okay. And let's recall convolutional network. For convolution kernel, we only see the surrounding pixel, right? Okay. So what they want to do is to mimic the convolutional network, just reduce the computational load for transformer. And this is their result. Okay. So if they use convolutional network, okay, they will get some accuracy for some. Okay, I should say, ResNet is a very effective CNN-based classification. And if they replace some layers in the ResNet by transformer, they will improve the performance. And for different ResNet classifier, the results are the same. So it means from this paper, they want to show that transformer can be used to improve performance of classifier based on convolutional network. And for another task for object detection, okay, they also show if they use the local attention mechanism in some existing method, they can reduce the computational load and reduce the number of parameters and generate a similarly compatible performance. Okay. So in this paper, they show this is the emerge of transformer in the computer vision field. Before this paper, most transformer is just a method for translation problems. Okay, then another paper is relation between self-attention and CNN, and let's go back to the slide. it is this paper. It was just published a few months after the attention in vision. Okay, so the importance of these papers, they prove in mathematically convolutional network is a simplified transformer. Okay, so this is their proof. So this is the definition of self-attention. That is the mechanism used in a transformer. Okay, so this is the definition of attention. So this is X. X is the input of sequence if we rearrange them as a metric. So this is WK and WQ, just show in the previous slide. And then with positional encoding, so the P is the positional encoding. And with multi-head self-attention, then it will write in this form. And then with several derivations, they will show under certain conditions, the multi-head self-attention will be this format. So are you familiar with this format? It looks like a very convolutional neural networks, right? So the importance of this paper is they show convolutional network is just a format of translation of transformer. Okay, so let's take a break. All right. Okay. So that's the platform I was looking for in previous class. That is a Dream Studio. Okay. So it is a platform. You can create images from your prompt input, and you do not need to install anything in your local PC. So this is an online service. Okay. And the stability, the AI, the company want to make money from the platform. They want to serve users. Okay. All right. So let's go back to our slides. Okay. After proving convolutional neural network is just a simplified transformer, okay, they did experiments on the CFR10 dataset, use ResNet 18, okay, and they show the results. So the y-axis is the test accuracy, the higher the better, and they try the original ResNet 18 and 3 versions of transformer, because transformer, since convolutional network is a simplified transformer, ideally transformer can cover everything for convolutional network. But from their experience, they found yes, if they try train the network for many epochs, your convolutional network, I should say, ResNet 18 performs better than transformer. Why? Okay, so the reason is here. That's, as you say, okay. This is their paper, relationship between transformer and I should say, transformer and convolutional network. And then within a year, VIT was released. Okay. And the VIT, in the paper for VIT, it shows, yes, this is true. But if you increase the dataset size and with some modification, transformer will perform better than convolutional network. So on the relation between transformer and the convolutional network, they did experiments on CFR10 dataset. And in the VIT paper, they run the same experiment on a very, very large JTF dataset. The JTF dataset is a Google private dataset. Nobody else can use it. And it has 300 million images in a data set. So it's very huge. They use different resolution. So on the relationship paper, the image size is very small. So this is large. And they also use different patch size. This is 2 by 2. And this is 14 by 14 or 16 by 13. And okay, so the number of images, they are only 0.6 million, and they are 300 million. Then, okay, this is the beginning of region transformer. Okay, so they use the transformer mechanism, but however, here they use patch, because we say the computational load for a transformer is the quadratic term of the n is the length of the sequence. Okay? If we use pixel as the input, then it will be very huge. But if we use patch means 14 by 14 or 16 by 16. So that given an image, we can crop it into several patches. And how long? Let's see the setting. If the image size is 227 square, and the patch size is 14, then how many patches will be in a row and in a column? It's around 16 or 15. It will be not very huge. And then the square of so therefore the length of the input vector will be around less than 300. Okay. Therefore, they can compute it using, although use a lot of GPUs, it is computable. Okay. So that's the reason. So let's see the proposed method. Given an image, they crop the image into several patches. And they create a classification token. It's a special code. They need to learn the token. However, it's just a token. And they use a linear projection to convert those patches into a vector. And they add the positional encoding 1, 2, 3, 4, 5, 9. They are also vectors. They combine those vectors and feed the sequence of vector into a transformer. So the transformer look like this, almost the same, actually totally the same as the one used in previous paper, the relationship. Okay, and then we say the input of transformer is a sequence of vectors, right? And the output is also a sequence of vectors. So in the last layer, there should be also a sequence of vectors here. And then they ignore all other vectors and only use the first vector. So if for the first vector, they learn another fully connected layer, and they can use it to pre-generate the probability of the classes. So, okay, the algorithm is just a few equations. So this is input image. They create patches, okay, and when they have the patches, they will learn patch to vector linear transformer E. This is learned. And for every position, they will also learn embedded vector. Okay, and they combine the two together plus the classification token. So this is the input sequence of vector. And then this is a mechanism, attention mechanism, and it goes through it a lot layers, layer by layer, layer by layer. And then finally, okay, so this is the finally generated sequence of vector, but they only need the first one. Use the first one, and through a linear normalization, layer normalization, they get the final vector D. Okay. So they use the final vector V to predict the class of the image. It's very similar to when we use ResNet, right? ResNet is layer by layer, and finally we will get a presentation of the image. And then we use the presentation vector of the image to predict the class of the image. Okay, so because there are different there are several parameters. For example, how many layers they can use, and what is the size, and how large is the fully connected layer. So they create 3 different settings: VIT base, VIT large, and VIT huge. The number of parameters are shown in this column: 86 million to more than 600 million parameters. Okay, then it is difficult to train. So if they use the TPU-V, so this is the tensor computation unit. It's like a GPU but more powerful, and it takes many days, 2,500 days to train a model. Okay, so they train their models. For example, this is a VIT huge, and the 16 means the patch size, 16 by 16. Oh, sorry, 14 by 14, then 16 by 16, and then they train those models and apply it on some existing data sets. They get the accuracy result. All right. So let's see a comparison. So see, this BIT means big transformer. It is an existing convolutional neural network, CNN-based method. Okay. And this is the VIT is transformer-based method. If they train the method on a small data set, for example, EGNet, then BIT performs better. So you see a range here. This means even for BIT, there are several different settings. Okay. So most of the settings, it performs better than transformer. But if they increase the data set from ImageNet to ImageNet 21K, ImageNet only then the performance are similar. The range covers each other. And if they train the transformer on a huge data set, the JFT300M, then okay, they found the VIT huge 14 data set created the best performance than any settings of BIT. So, and okay, from another setting, so they compare different numbers of JFT images. This is if they use all of them, it will be 300 million. But if they use only partial of them, it can be 10 million, 30 million, or 100 million. Okay, so they see this is the performance. Okay, if they use more images, for most of the performance, they work better. And compare with this is the ResNet, the largest BIT setting. They use ResNet 152 layers and use 2 ResNet combine them together. Okay, then this is the performance of BIT. In the beginning, if they use just 10 million images, BIT works better. But if they use 300 million images, transformer works better. Okay, so it means what? It means it means CNN is good for relatively small data set. A transformer is good for huge data sets. Okay, so this is their conclusion. But however, it is very expensive to train transformer. So the x-axis means the training cost. Okay, and the unit is exaflops. So exa is so this is the unit giga, tera, peta, and exa. This is very, very huge. And here we can see to train a very, very good transformer, it takes so much computational load. It's difficult to train. And let's show some visualized token. So this is the first, the embedding layer. The embedding layer means this. Okay. Here. Okay. So this is the embedding layer E. Okay. And it was used in here. When we have a patch, it will convert the patch into a vector. So this is the embedding matrix. And if we visualize the embedding matrix, it will look like this. Okay, if they just show the first 8 most important one, okay, it will look like this. It means what? Given a patch, the trained transformer, they will convert the patch into some meaningful vectors, minimal signals. Meaningful for what? Meaningful for classification. So it is very similar to the first layer of ResNet. Remember, for ResNet there are several layers. So the early layers learn edges or in particular strong contrast, and the middle edges learn some details like texture, etc. And the later edge is more the overall shape of some objects. Okay, so for transformer, they works almost in the same way. The first layer learns it is difficult to say what does it mean. For this, it looks like do you remember the Sobel filter? Oh, okay. So and this is also looks some Sobel filter, but for different direction. Okay. All right, and this is the position embedding vectors. They are used in here. This is the position embedding matrix. It means for every patch, it will, this is the transfer the vector, and it will plus a positional embedding vector. And the positional embedding is also learned. And let's see the result. The learned embedding system looks like this one. So this is if given an image, and it was cropped into 7 by 7 patches. Okay, then the position embedding will be they compute the similarity between one position embedding vector and another position embedding vector. So for position close to each other, their similarity should be higher. Okay. So let's see. For this metric, you can see the brightest pixel around this area is at the left top corner. It means it's a self. Okay. And compare this and to this, you can see the yellow pixels move from left to right. Okay. So what is the meaning of this figure? It means given a lot of images, the transformer effectively learn the location of those patches. So this is the meaning. And if we use the learned, so finally the transformer will generate a vector to present the image, right? and the vector will be used for the as a classifier. And if we extract the picture and try to go through to the image layer, so it will like as well. Given this input image through the learned transformer, and the transformer will see what is the important message in this image. It will highlight this region. So it means this is a class of dog. The transformer will ignore some other unimportant region in the image, like the grass or the sky. It is not related to the dog. And for the airplane, it will also learn this is the important message. So, okay, so this is snake. It will recognize this region. Okay. So from this paper, Google, they have shown vision transformer is very, very powerful if they can have sufficient image to train the VIT, vision transformer. But then we need to answer another question. Why is CNN so useful if the data is not very large? Okay, this is their answer. CNN is a method to learn some neighborhood structure in the two-dimensional space. So there is a term called inductive bias. It means when CNN, the method was invented, the method originally tends to learn local structure. Therefore, when the image set is not very large, there are only, I should say, 100,000, like ImageNet. Okay, then the local structure is very useful information to recognize, to classify those objects or those classes. So you see, this is the illustration for CNN. It looks information locally, and finally generate the presentation of the image. And the benefit of the local structure is if you move the object from one location to another location, for example, this cat, then the CNN will also generate a similar result. Okay. But however, for vision transformer, it doesn't work in this way. Vision transformer, you see, the input sequence means what? Means the whole image. And through layer by layer, it means vision transformer will look all information, not just locally, even somewhere far away. Therefore, vision transformer is difficult to track, difficult to learn, but it is more powerful if you have more images. Okay. There's another paper, ImageNet trained CNN are biased toward texture, and this paper was published in ICLR 19. The paper shows the same thing. Okay, let me see. So this is the texture of elephant, and this is a cat. If they use style transferring method to generate this image, then the CNN-based method will predict this is an elephant rather than a cat. So the probability to an elephant is 63%, and for a cat, no, not in the list. So what does it mean? It means CNN learn the texture. What does texture mean? Texture means the local structure or local relationship between those pixels. And this is another example. If this is the original image, and there are some widely known convolutional-based method, AlexNet, GoogleNet, VGG16, or ResNet, and human, then those CNN-based methods predict the image very well. If they translate to grayscale, they also works very well. But if the image was translated into silhouette, then their performance become worse than human. If the image translated to edges, they even works very worse. But CNN-based methods are very good for texture. So this is the support to the answer. CNN learn local structure. Okay. All right. Okay. So this is the first track for transformer. Okay. Then I'm going to talk about oh no, I just said I will go to talk about CLIP. But before going, because CLIP use vision transformer. But before going to CLIP, I want to talk about something about image data set. Before you see, say the Google's private data set uses 3 million images. No, 300 million images. And there are some efforts to create a large data set. So in 2011, the largest data set is the SBU1M data set. There are only 1 million images. And in 2016, the largest data set is the YFCC 100 million. The YFCC means Yahoo, Flickr created to command data set. It means you know Flickr. Do you know Flickr? Flickr is a website. Users can upload their photos to the website to share with friends, okay, or just make it publicly available. And there are many licenses. The Creative Commons license means users can download it and use the photos for any purpose. They don't care about it. Okay, so then there is a list you can see from many years ago to 2015. Okay, the largest data set is this one, YFCC 100. The size of image is around 100 million. Okay. And now I'm going to talk about CLIP. Okay, CLIP is a method. It is a synonym for contrastive language image pre-trained, proposed by OpenAI. And they report their method in this archive paper. And the paper was also published in ICNL 21, so just 2 years ago. So this is a quite relatively new paper. So what do they mean? Here, they prepare a very huge data set. There are 400 million image text pairs. And for every pair, okay, they have a sentence. So in this example, paper, so this is dog. They use a text encoder to create a vector to the sentence. And the text encoder here is transformer. So this is the relationship between transformer and the CLIP. And because this is a text image pair data set, if there is a sentence, there is also an image. So from this image, they use the image encoder to create a vector. So the vector should be paired. Okay. And from a batch, so from the 400 million instances, they just randomly crop a few instances as a patch. And in the batch, they will compute the dot product of the text vector and the image vector. They want the value of the dot product are highest on the diagonal lines. You got the sense? The vector, a vector is from its sentence. The vector is from its image. If they are well trained, then the two vectors should be similar to each other. And the dot product should be higher than any other element on the row and in this column. So the method is quite simple. The difficulty is how to create a high quality, huge image to text dataset. And because this is OpenAI, and OpenAI, they I should say, they were very brave. They just like to do research in this way, create a very huge data set, and become a very innovative approach. Okay. Then, all right. So, okay, let's see the comparison here. So they created the data set. How do they create? Okay. They send 500K queries. Queries just like keyword, dog, cat, desk, offices, book, etc. And then from internet, they can retrieve a lot of sentences and images. And they need to, okay, I should say, they keep a limitation for any keyword. For a keyword, they will only allow 20K images, so that the dataset will not be biased to some keywords too much. Okay? And totally, they collect 400 million pairs. Okay, and then they use transformer and some image ResNet, VIT, and Diffusion to train the image encoder. And they train it from scratch. They use 18 days on 292 V100 GPUs. So you can see the computation load is so huge. Okay. And the largest image encoder is VIT large, and with 14 by 14 page size. And the input image is 336 pixels. It requires 12 days to train on the 256 V100 GPUs. So they spend so much time, computational load, and money, because to train those models, they need a lot of money to do it. Okay. So, and they released their pre-trained model. So let's see a comparison. For different lines, it means different settings. Okay. The best one is they use VIT as the image transformer, and they use the trained CLIP model. So what the CLIP model means here? This they call the text to vector encoder CLIP model. Okay, so you see the combination VIT and CLIP achieve the highest average score for 12 datasets, the average of them. It means what? It means if they have so many image text pairs, and they can use VIT and transformer, they can generate a very, very effective text to they can create a very effective text to the embedding space vector. Okay, and they do the experiment for linear prop. Linear prop means if they have they pre-train a model using a data set, and then they replace the final layer of the pre-trained model, and then uses another data set to fine-tune the fine-tuned model, become a new classifier. Then, okay, let's see. So AV dot here means classification. So you know is the M list. So this is the you know. And the CFAR10, you also know it here. And some other data set, which do you know? Okay, ImageNet data set is here. So you can see they use the pre-trained CLIP model, and then they just fine-tune the new data set. They can significantly improve the performance. So what does it mean? It means their method, they want to claim their training method is very effective and useful. Okay, so this is another, they show this image to claim. Okay? So what does it mean zero-shot performance? It means they train their models on the CLIP for 100 million data set, and the encoder never sees any images from those data sets. Okay, so they just use the pre-trained data set and apply it on the new data set. This means zero shot because it's never seen any examples from those data sets. Okay, so they show that for example for this CFAR10 data set, even though the pre-trained CLIP classifier never see any images in the CFAR10, it can still generate better results. Okay, over what? Over data set pre-trained over the ResNet 500 classifier and pre-trained on the same data set. Okay, let's explain. So there are two settings. One is you use the CNN-based ResNet 500 data set and use the CFAR10 data set to train. Okay, you can get the performance. Okay. Another case is you train the CLIP classifier on the CLIP 4,000 million data set, and just frozen those parameters and just replace the last layer, and use the same CFAR10 data set to fine-tune the new last layers. And okay, you compare the two results, and it shows from this figure the CLIP data set works better than the ResNet 550. Even though all of the parameters in the CLIP data set are frozen except the last layer. So it means what? It means after learning from the 4 million just image to text data, there is no class information in the CLIP 400 million. There are only text and image. The trained data set has no idea what a class is. They just know some image are related to some text. That's all. Okay, and the learned knowledge is very useful when the model is applied for a classification task. Okay. All right, so here is the zero shot. The performance for 20 classes, 20 dataset average, and this is zero shot. And then this is linear probe, just fine-tuned performance. So it means if it knows nothing about those datasets, it can still generate the performance around 63%. But if you use ResNet 550 and you tune it, then the performance is still worse than the CLIP dataset. So it means what? It means CLIP in classifier is much effective than the ResNet 50. Okay, so there are some examples. So for each image, you can see it means the image is cropped from data set. So there are at least 12 different data sets. Then, given this image and given several sentences, the CLIP encoder, image encoder, and text encoder can find the best match. So, given the image and the several choice of sentences, it will show this is the best, the most matched combination. Okay, and this is another example. Banana, the class of images. In different data sets, they have different appearance. So this is for ImageNet. All of those images are from the banana class. But there is an ImageNet version 2. So this are the images. And the ImageNet rendition. So the ImageNet rendition dataset is created to show how effective the classifier would be if they see something very, very unusual from the existing dataset. Okay. So you can see all of them are banana images, but they look quite different from the original ImageNet dataset. And also there is an ObjectNet banana and the ImageNet sketch dataset, and the ImageNet A means art dataset. So there are bananas in those images, but those images are very different from the image dataset because they are, should say, art. They look like art result. Okay, so here, the point is, if they use ResNet 101, it's a very large classifier, and train it on the image dataset, and apply the result on other datasets, this is the performance. So it makes sense. You see, they train images they train the classifier on the image dataset and apply on the image dataset. So the performance is around 76. But if they train images on ImageNet and apply the classifier on other datasets, because the test images are looked different from the training images, the performance become worse. But however, CLIP, or even though CLIP never saw those images, CLIP only know banana or some words related to banana in its 400 million dataset, and then apply the trained method with the linear probe method, then the performance is much better than the ResNet 101 method. And this is the difference between the two scores. So it means what? It means CLIP looks like something, like it's somehow like a human, because it saw so many images and learn them from those text sentences. Now let's show how other researchers use the CLIP. So this is the CLIPDraw. It was published a few months after CLIP. Let's see their time slide. So CLIP was released here. And the CLIPDraw was just released around 3 months later. So CLIPDraw is used for what? So let's explain the idea of CLIPDraw. Given a sentence, and with CLIP model, we can generate the text embedding, just a vector, and randomly generate some stripe or just some curves, and we use CLIP text encoder. So we will generate another vector. We compute the similarity between the text encoder and the varied image vector. So it will so if the image can express the meaning in a sentence, then the cosine distance will be very large. If not, then the cosine distance will be very small. Then there's a loss function, and iteratively repeat this sentence. So this is an augmented batch. It means given an input image, it will several randomly noised and randomly distorted result. And within every iteration, they will pick up the one mostly match the sentence. So this is iteration. In the beginning, it's just almost like a random. And through 10 iteration, 30 iteration, and 250 iteration. So the image looks like the message of the sentence. So this is the application for CLIP. So let's see some results. So given a sentence, a drawing of a cat, their method can generate an image. Horse eating a cupcake like this. So yeah, you see, what is this? This is a text to image generative model. And they also show that given the sentence, the subject is a cat, and use the method. Just use the pre-trained CLIP model. Their generated images can express the message with different styles. And then they also show the negative prompt. So here you can see they given a sentence, but with the negative prompt, they can generate the expected result. And when you use stable diffusion, I remember some of them use the negative prompt, right? If you want to get a beautiful, elegant image, you can use negative prompt, ugly or bad, in the input prompt. So CLIPDraw has shown that CLIP can do it. Now after CLIP, researchers found that, it's so powerful, but the dataset was private. We cannot play with them. So LAION project, they want to create, their goal is create a 100% free, publicly available, and a large scale image data set. And then they just crawling through the internet, found any image tag, and then download. No, they don't download. They just create a very, very long list. The list covers the URL of the image. And okay, since there is the image, how do they recognize the sentence or text from the image? There are two ways. First, if there are some description, because when you write an HTML, right? If you have an image tag, usually there is a text description of the image. They explore this information. And the second way is, if they have the image, they apply some OCR method to recognize sentences in the image. Okay. So they first release the LAION 400 million data set. And several months later, they released the LAION 5 billion data set. So the 5 billion set, there are, okay, 200, right. Let's take a break. All right, so from the LAION 5 billion data set, you can see this. Half of, I should say, 2.3 billion are English. 2.2 billion are other 100 plus languages. And top 5 are Russia, French, German, Spanish, and Chinese. And there are also 1.2 billion images without a text sentence. Okay. So what we need to do care about the LAION? Because when we use stable diffusion, the version 2.0, it uses OpenCLIP trained from LAION 5 billion. And stable diffusion starts from latent diffusion. Latent diffusion is a multi-purpose model for the text-to-image task. It was trained on LAION 400 million. Right. So this is the content of the LAION 4 million data set. So there is the index, the URL of the image, the text string, the height and the width, and the cosine similarity between text and the embedding. So how do they create this? They use CLIP. They use CLIP to create, because CLIP released their pre-trained model. So they can train the similarity between text and the image. And they also provide an interesting score, means NSFW, not safe, suitable for work. So it's what, because they got images from internet, and there are many images full of, for example, porno, okay, violence, and criminal or discrimination images. Okay, so they also provide this score. So this score is sometimes useful because if we want to create a child-safe image to text-to-image generator, okay, then we can either use this score to prevent some image sources, or if we generate the image source, we can use the score to learn a discriminator to predict, well, what's the label of the NSFW? Okay, and there are two subsets called LAION high resolution and the LAION aesthetic. So the two subsets was used to train. Let me show you a figure first. Was to train. Okay. Okay, here. Okay. So stable diffusion comes from latent diffusion, and there are several models. So here you can see the model 1.3 and to 1.4 were trained on the LAION aesthetic subset. So that because they use the aesthetic images, they capture the images with better aesthetics. Okay. Okay, so this is the first track. Okay, we talk about the transformer, and now we are talking about the diffusion model. Okay, so there are 4 important papers. I listed them here. The first one is DDPM. Okay, so the full name is denoising diffusion probabilistic model. All right, okay. So what is diffusion model? It means given a clear image, and in every step, if we add some noise into the image, then finally the image will become just noisy image. And now we want to develop a method. Given a noise passage, we will step by step and go back to the clear image. Okay, so it's very like GAN. When you use GAN, your input is just a normal distribution, and with your trained generator, you will create many clear images. Okay, but there is a discriminant in the GAN architecture, but there is no discriminant in the diffusion model. So this is a definition. It means given a clear image x0, and in each step, the new image xt only depends on its previous image xt minus 1, and their relationship is a normal distribution. Okay, and the variance of the distribution is beta t, and the mean will be slightly 1 minus beta t squared. So it means what? If you apply the equation many times, your noise will be mean as almost 0, and the variance is almost 1. Okay, it's very like a noisy input, a noisy image. Okay, so this is just they in the DDPM paper, they just created 2 symbols, alpha t and alpha t bar, like this. Okay, and then because this for every step it is a normal distribution, so we can predict so I should say the distribution, the probability of xt or the distribution of xt based on x0 is just another normal distribution, and the mean and the variance is square alpha bar t and 1 minus alpha bar t. Okay. So that given xt and x0, if we want to predict its previous state, so it means from now, given this x0 and xt, if we want to predict the xt and the less noisy, so this is the denoise step. Okay? So it will become another normal distribution, and the tilde t, tilde mu is in this format, and the tilde beta t is in this format. So your question, how do you get equation 6 from equation 4? And this is the proof. So okay, I just assume. I should say okay. I show the derivation here, but we want to spend time on it. Okay. So the diffusion model want to learn xt to xt minus 1. So this is the noise. We will step by step to go to the clear image. If we express the equation here, it will look like this way. This is a normal distribution. And in the normal distribution, we want xt, if we define a loss function here from the normal distribution, then what the most important message is, because this is a normal distribution, so what we should select from, if we know xt minus t, and we want to select one of xt minus 1, we should pick up the value with the maximum probability. Okay, right? Okay. If you therefore the DDPM, they propose to learn this. They want to learn this. It means the maximum probability of the normal distribution. Okay. So therefore they want to learn a value. The epsilon here means the noise, okay? And the epsilon theta means the network. They can learn. If you have the x0, the clear image, and you have you know the beta steps, just from beta 1 to beta t, so that you can calculate the alpha t bar. Alpha t bar is just by definition. This is the definition only. This is a product of many alpha s, and alpha s is defined as 1 minus beta t. So given xt, and you can calculate the alpha t bar square, and also you can calculate the E minus alpha t bar, and you know the random noise and the step t. Then you DDPM propose to learn the relationship. So this is where they give. So this epsilon t, you can imagine, is just a U-net, and the U-net you can give the t and the image, the noise, the image into the U-net, and the U-net should learn the given noise. So this is the convolutional network. Given noise, image, and step t, it should learn the noise. Okay. Then, when you learn, if you get a very good U-net there, then in the sample time, given the noise, then you predict the noise from your network and then apply the step, then you can get the clear image. Okay, so let's see the experimental setting. They said there are 1,000 steps, and the beta from 0.1 to 0.02, and this is linearly increased. This is just an assumption, okay? And then use a unmasked pixel CNN plus. This is a network proposed, U-net based proposed by another researchers. Okay? And they train their models on a TPU V3-8 machine. Okay, and this is a setting. They trained for CFA10, Celeb AHQ, and for those data set, they set those image size, and this is a number of their parameters. They train the diffusion model for those steps, because this is a training step. They will stop. They won't stop anytime. So they just stop at the number. And for the the smallest data set, it takes 10.6 hours to train it, to train the 800K steps. So this is the result. So this is the CLIPDraw HQ, and this is the CFA10. It looks very like GAN. Given the noise, you can create images. So this is the result of the DDPM. It's just a diffusion model. And there are some quantitative comparisons. So for DDPM, for the LSAM bedroom data set, okay, their performance are worse than CellGAN. You know CellGAN already, right? The NVIDIA Teams result. And for LSAM Church and LSAM Cat, so this is FID. FID, the smaller the better. Okay. Their results are not as good as the existing GANs. And for the CFA10 results, they also report for. Okay, so this is their result. Their results are not are the best one just for CFA10. Okay, and there are no other reports in this paper. But in addition to GAN, although their performances are not as good for the LSAM Church and LSAM Cat data set, their performance is good in the CFA10 data set. Oh, it attracts a lot of researchers. They want to understand why this method works. A few months later, so DDPM was uploaded in 20 February, and then another paper was released. So just 8 months later, okay, another paper was released. So this is they use totally the same mathematical assumption. It means they just follow DDPM's equation, but they assume, they consider if they know the x0, okay, then they can use x0 and xt to predict xt minus 1 in another mathematical expression. So they created this mathematical expression, and here the sigma t is a variable for any positive number. It works. Okay, and again, you may ask, from the DDPM's definition, how do we get the equation 7? Okay, this is the mathematical derivation for equation 7. Again, I want to spend. Okay, just keep it in mind. If you can look at the same equations on the paper, and I want to show you those researchers, they are experts for this area. So they list the equations. But here we just want to get the concept. So let's go quickly skip this. Okay, so what is this? From these equations, they can predict okay, what is it? For DDPM, they need to go step by step. From xt, they can only predict the xt minus 1. But the DDIM, this method, they propose from xt, they directly predict x0 and use the predict x0 to formulate another equation. And from this equation, they will get the xt will be xt minus 1, and xt will become this relationship. So let's see the experimental setting. So they use the same setting as the DDPM. And here is, in DDPM, it needs 1,000 steps. Okay, but for DDIM, they can reduce the step from 1,000 to 100 to 50 to 20 to 10. So it means, okay, and then see their result. They set a hyperparameter eta here. If eta equals 1, it is DDPM. So this is the result of DDPM. And eta equals 0, it is DDIM. So this line is the DDIM. For CFAR10, they tested it on 2 data sets, CFAR10 and SLAP8. So for DDPM, okay, and the DDIM, they show under totally the same setting. Just use different algorithms to predict the same model, okay, and then their results can be they can generate a better result if the step is less than 1,000. So it what does it mean? It means they can achieve similar or better results, use less computational load. It's something like when we were elementary school students, we need to calculate 1 plus 2 plus 3 plus 4 plus 5 plus 100. What is the number? Okay, so for some students, you just need 1 plus 2 equals 3, 3 plus 3 equals 6, 6 plus 4 equals 10. Okay, this is one way. Another way is, if you know the relationship, this is 1 plus 100 and the time, the number, and divided by 2. This is, we will get the same result. It's very similar like DDPM and DDIM. So we can see DDIM is improved or accelerated method from DDPM. Okay, there are some experimental results. So for different steps from 1,000 to 10, this is generate the images. And again, for different steps, so you can see when the number of steps is very high, so it's about 1,000, the generated image looks quite good. But if there are only 100 steps, then the quality is still acceptable. But if there are only 10 steps, then the quality becomes blurred. Okay, it's not as good as the one. So that's the meaning. If you only have 10 steps, your FID value is 13. But you have 100 steps, your FID value is 4.16. It's closer, much closer to the setting of 1,000. So what does it mean? DDPM use 1,000 and get the result of 4.73. And if we use DDIM, we can reduce the number of steps from 1,000 to 50, and the FID values are almost similar. And they also show that for DDIM, if they want to train more steps, then the required computation load is linearly increased. Okay, so this is not good or bad. It's just show a fact, and that for other researchers, okay, they think no problem. Okay, if I want to get a better result, I just train them with more training computation load. Okay, then let's see another. Let's go back to the time chart. So let's from DDPM to DDIM. Then OpenAI published 2 papers. One is improving DDPM. Another is diffusion model bit gains. The 2 papers further improve DDIM and DDPM, and let's see how they did it. And the 2 papers comes from the same 2 authors. Okay. So the 2 authors are Nico and contribute equally to the two papers. So they just randomly arrange the order of the first author and second author. So if you see the second paper, it will look like this. Okay, I didn't show it. Okay, that's fine. So the two authors challenges a few questions. First, why is the noising, the level of variance linearly increased? Is it the best setting? Okay, and they found no. They can propose a better schedule to improve the performance. And why the equation in DDPM is equation 8? It means it's a L2 norm. Okay, they found if they use another norm LVB variational lower bound, the result will be better. So let's see. First is the schedule. So this is a linear schedule. The blue line, it was used in DDPM. So the result will look like this. This is the alpha bar T. Okay, so it means in the almost it increased very quickly. Okay. And the OpenAI team proposed the cosine schedule. So let's see the comparison here. The upper row is the linear schedule. So in the middle, there are a lot of noise. And this is the cosine schedule. So in the beginning, you can see clear image from this to this. Okay. And they show if they use the cosine schedule, then the FID is much better than the linear schedule. And if they use the VLB loss, then they can also improve the LN. This is another metric called negative log likelihood metric. Okay. A few months later, they ask another question. In DDPM, they use the pixel CN++ as the U-net to learn noise from the given image. Is it the best choice? Okay, and they question it because there are two existing papers. This one, and this one. The both papers mentioned if they tune the architecture of the U-net, DDPM generates better result. Okay. So the OpenAI team, they want to, okay, so let's see. This is the second paper. Okay. In the second paper, they show a table. So this is the DDPM, original DDPM. Okay. And if they modify it in some way, and they create a new structure called DDPM++, then the FID value becomes smaller. It means better. Okay. Okay, so the OpenAI, they try to improve the pixel CNN++, the U-net, okay, from those directions. They want to increase depth rather than width, okay, but they keep the size of the U-net approximately the same. They want to create the number of attention heads. Okay, they want to use attention on more layers rather than just a single layer. Okay, and they want to apply some existing method. For example, the 16 is this paper. Okay, and they want to apply some small modification to see whether they can improve the performance of DDPM. But here, I need to show you what is pixel CNN++. Okay, so you know this is a U-net, and this is the U-net proposed by pixel CNN++ is from OpenAI, the set from OpenAI. Okay, I'm not sure OpenAI or Google. Okay. So, however, this is the UNet. From the beginning, there is a 32 by 32 downsampling to 16 by 16, so 88, and then it's upsampled to 828, 16 to 32. Basically, this is a U structure, and this is steps. From the first track, they will use the several ResNet block to create another track. So this is the depth, means here. And okay, so this is 32 to 32. In DDPM's implementation, they create a connection from 16 to 16 to the upsampling 16 to 16 through a transformer. So the OpenAI team questioned if we had other transformer connection from 32 to 32, A to A, rather than just use a single 16 to 16. Will it better? So this is their experimental results. Okay, so this is the DDPM's proposed, and they try to increase the depth. Okay, the FID decrease. They increase the number of heads. This is the structure in the transformer. Okay, it also decrease the FID, and originally attention was only used on the 16 by 16 layer. If they use not only 16 by 16, but also 32 by 32 and 8 by 8, it also decreases the FID value. And if they apply the big gain downsampling, it means use the square of the dimension as the denominator. They found that yes, it works. The FID also decreases. But if they try the rescale race block, no, it doesn't work. Okay, so they found, okay, yes, the network can be tuned, and it will generate a better result. They also try different settings. So this is an adaptive group normalization used by DDPM. If they try another setting, then they found no, it doesn't work. The FID increased. Okay, so they try different settings, and okay, they found it works. It helps. Even use the same DDPM model. After tuning the networks, they can increase better results. So there are many different settings, and they found when they draw the FID against the training hours, they found that some settings are very useful. Okay. All right, and they also found interesting things because I should say, when the method DDPM was proposed, the DDPM didn't consider the conditional sampling. Conditional sampling means, let's recall DDPM. You give a clear image and generate the noise, and now you want to generate a clear image from the noise. Okay, this is a denoising process. Here, you not only want generate a clear image, you also want the generated image contains a dog or a cat. This is conditioned by label. So this is so the OpenAI team, they try the conditional sampling for DDPM. So it means this is from xt plus 1, the noisy, and we want to predict a slightly clear image xt. Here, we need to consider a condition label. It's just a y. Y could be for example, if you use ImageNet, so then Y means banana, dog, cat, and car, etc. Okay. Now they want to study how to model the probability, so that given when a label is given, they can generate what is the DDPM step from xt plus 1 to xt. Okay, so by definition, this is the probability of xt given xt plus 1 and label y. It can be derived to this format. So this is the z here. Okay. So given I show these equations here. I want to just want to show you how do they get the right part of this equation. It is the constant times. So this is the original DDPM part, right? Just there is no label used, and this is the what? This is the classifier. Given an image, even it is noisy, and we want to predict the label from the image. So this is a classifier. So conditional sampling for DDPM is a combination of DDPM and a classifier. Okay, so by definition, this is a DDPM definition, and because it's a normal distribution, it can be rewritten as this format. When they use Taylor expression to expand this equation at the location of xt, it will look like this. So they will, after a few derivatives, this probability will become this. So, okay, let's skip it to the conclusion. The conclusion is, if you want to use DDPM for conditional subsampling, and you have a classifier already, then you just use this equation. It means given xt plus 1, you predict the xt as the mu plus the sigma times g. And g is what? G is the gradient of the classifier. And what is sigma? Sigma is the variance of the distribution. Right? So the message here is DDPM originally doesn't consider class label. But OpenAI, when they consider class label, and they found it's not difficult. If you have a classifier, and you can get its gradient, right? And you can also get the variance of the distribution. Then it's very easy. Just use this equation. You can generate images contain the class you want. Okay, so in the OpenAI paper, they propose, or not propose, they explain their algorithm in this way. So this is very, very similar to DDPM. The only difference is they have the class, the gradient of the classifier term. And they also found that if they scale the gradient here, right, they can create some images very useful. So that means, what does it mean useful? Okay, let's see. So if they use the scale as 1, then and scale up as 10, the FID decrease. Okay, and their inception score increase. What is inception score? There is a inception net. The inception score is used to, if you have a lot of image and put them into an inception net, how well those images will be classified. So inception net higher means, yes, your generated images match the expected class. Okay. So let's see the result. So for the left side, they use the scale as 1.0. It's a small scale. Okay. And all other settings are the same. And they want to generate the class of Corgi. So we still can see Corgi here and there. But if they use the scale number as 10 times larger, they will generate those images. Both of them are Corgi images. But here we see a very obvious, very clear Corgi. So this is why I say they found, if they tune the scale vector, it's very useful to generate images used as what. Okay. So when you use stable diffusion, you also see the scale vector. Let's go here. Okay. This is the scale vector. So if you tune the value very small, the smallest value you can set is 1.1, and the large is usually the default value is around 10, and you can also try a very large value, and the meaning is the meaning is in this algorithm. Okay, so they call their method for ADN. It is a blended diffusion model, and they compare their method with some existing method, and then it shows they generated the best FID, spatial FID, and precision result. Okay. But however, the problem of the ADN is the computational load is very, very high. To train a model, it takes so many days on a single GPU. And to generate 50K images to compute FID, it also takes so many days. So the computational load is very high. Okay, so that's the motivation for stable diffusion. Okay, so we saw this slide before, so let's skip it. And this page shows stable diffusion or latent diffusion. It is very attractive. So let's see this figure. This is the number of days when the model is released. It compared with this is bit count. So it means, and this is the GitHub data. It means when bit count was released after say 1,000 days, and there are how many people follow it. It means when stable diffusion or latent diffusion was released just in 30 days or 50 days, a lot of users follow the GitHub project. Okay, and we saw this. And now we are talking about the latent diffusion. Okay. So this is given an image. The image will be converted into latent space through an encoder. And there will a lot of noise will be added here. So this is a noised latent vector. Okay? And if we use text as a prompt, then the text will be encoded by a text encoder. And in different versions, for example, 1.0 to 1.5, they use CLIP text encoder here. And for stable diffusion version 2.0 to 0.1, they use OpenCLIP. This is another text encoder. When they get a text encoder, it will be inserted into several attention mechanism as the V and the K metric. And the diffusion, the noise, or I should say noise, the latent variable will be used as the Q query matrix here. So this is a close attention mechanism. One from condition, another from the latent variable. And finally, they will generate a new latent variable and denoise. Denoise just like a DDPM. It is step by step going back. And then the reconstruct the latent variable will be used in an image encoder, and then finally generate the reconstructed image. So this is the process, but we need to explain the third part of this diffusion model. It is the variation, the encoder and the decoder. So I will go start here. What is autoencoder? The definition of the algorithm is that you give a signal, and there is encoder, and you convert the signal into a latent space. And then the decoder, it will reconstruct the signal to your original domain. And you want the reconstructed signal X prime will very similar, almost the same as the input signal X. Okay. This is autoencoder. And the variational autoencoder means they want to control the latent space. Given a distribution of the input image, they want the converted latent vectors follow certain distribution. Okay, in this paper, autoencoding variational base, they propose let's make this distribution like a Gaussian. So how do they do it? They apply fully connected layers. So they use convolutional layers there. Okay, so that for the decoder and the encoder, and train those convolutional layers to learn the latent variable. So this is some example. How many steps of the convolutional network? If there are only 2 layers, 5 layers, 10 layers, and 20 layers, this is their generated results. And they show, okay, so this is the from any data set. If they can, their method can learn the change from one digit to another digit, because this is a normal distribution. They can control the latent code to generate the digit that they want. So for fixed image, the same. Okay, if they successfully learn the distribution in a latent space, they can create faces for left, for right, smile or not smile, up to them. Okay, then in 2017, VQ-VAE was proposed. VQ means what? Now, in VAE, they proposed to learn normal distribution in the latent space. And the VQ-VAE proposed to learn discrete vectors in the latent space. So why, you may ask, why do we need to learn discrete? Okay, for some models, it is this. What do you mean? What do I mean? Some things in the world are not continuous. For like what? Our language. Our language consists of many words, and from one word to another word, no matter English or Chinese or other language, they are discrete. They are not continuous. And for example, you know ImageNet, right? And there are many classes, for say 1,000 classes. They are not continuous. They are discrete. So that's the reason they propose the VQ-VAE. And they claim that, even though those latent variables are discrete. The reconstructed images are still good. And the loss is small. They also show another advantage. It means their VQ-VAE can be used to generate images by what? By this. This is pixel CNN. Pixel CNN wants what? It means if you only see a portion of the image, you want to predict the next pixel. And when the latent space is discrete, you can apply some method, for example, transformer here, to predict the next pixel. Okay. And they also show that if they learn, their VQ-VAE can do what? They can train multiple VQ-VAE for our voice signals, and then can keep the words in those signals the same, but it sounds very different. Okay, so this is the usage for VQ-VAE. Right, so that's all of our lecture today. And